Now we're going to move from the theoretical foundation that we've been building with probability and random variables to start talking about how we can gather data and use it to make conclusions about the world in general. And to do that, we are going to be looking at samples of data. And in this first video, we'll introduce some key terms that we'll use when referring to samples. So let's see where this fits into our data science life cycle. In order to use data to make some conclusions and help us better understand the world, we really have to examine how we obtained that data in the first place. So we're going to zero in now on this top right corner of the data science life cycle and look at how we obtain our data and how that can affect our ability to make conclusions from it. Up until now, we have been building a framework that we can use to help us describe what we're going to call a population. So I may be interested in, for example, the heights of all currently enrolled CU students for some random reason. There is some underlying distribution for the heights of all CU students. And in theory, if I could go measure every single student, I could describe that distribution perfectly. And I would be able to calculate probabilities and or things like the mean or the variance or whatever I may want to know. But in reality, it's usually not feasible, and sometimes not even possible, to get information from an entire population. And so instead, we can use information from a sample. And in general, what I'd like to do is be able to use the information from the sample to make what we call inferences, which are some predictions or our best guesses about what is true for the whole population. So this is the beginning of the part of the course where we're going to be looking at techniques for statistical inference. And in particular, some questions of interest that we'll examine during this time is, in situations where we can't observe the entire population, what can we infer from a sample drawn? How large does that sample need to be before your conclusions become trustworthy? And how do we mathematically express confidence in what we conclude? So a key piece in understanding the world is really zeroing in on how we are getting the data, or what the data we are using is capturing. Without knowing something about how the data was collected, there's not a way to make reliable connections between the sample and the population. Okay, so I keep using this word population. Yes, it can represent a set of people. Maybe I'm interested in some characteristic of those set of people, but I'm not limited to just thinking of a population in terms of people. Depending on whatever I'm interested in studying and making predictions about, my population could be bacteria in your gut, or plants of a certain species, or small businesses, or houses in a certain city, etc. In any of these cases, we might try to examine a sample and then draw inferences about the population. We see this most frequently in the news around election times, when we'll start reporting results of polls to try to predict how people are going to vote in a given election. All right, so let's look at some key terms here. A census, you will have, usually I hear the word census and I think of the US Census that goes around and counts all the people currently living in the United States. From a statistical standpoint, we're actually going to define a census even more broadly. It's an official count or survey of a population, recording details of individuals. Again, since your population doesn't have to be people, a census might be the heights of trees, of all the trees in a given area of interest. So again, just think of census as complete information about your population, or at least it's a way of gathering and recording that complete information. Survey is the set of questions that you use to gather that census. And I do want to highlight that what you ask and how you ask it can affect the answers you may or may not get, and whether or not you even get a response. There are entire courses on surveying and setting up your surveys in a way to try to eliminate different biases. And we will touch just on a few of the issues with this, but we will in no way cover the full scope of what goes into creating good surveys. Okay, so census is great, but typically it's not feasible, and sometimes it's not even possible. So a sample is what we use instead, and this is a subset of your population. So here you can see I've got this person in the sample, but the person next to them did not end up in the sample. Here, I'm just visually representing the sample by showing you which people from the population I sampled. Now let's look at the difference between some key terms we'll be using. Target population is the group you want to learn something about. I'm going to visualize these with circles here just so you can get a sense of how these sets may or may not overlap. Sampling frame or access frame is really the list of elements in your population for which you have access to. So it's not necessarily that your sampling frame will exactly equal the target population. Ideally, that would be the best case scenario. But for example, in the CU situation where I wanted to figure out the heights of students in CU, maybe I wanted to get an estimate of the average height of currently enrolled students, my sampling frame is really going to be the list from which I'm able to sample students. So maybe I'm using the directory that's posted online with currently enrolled students. And in that case, the sampling frame wouldn't exactly equal the target population because students can opt out of being in the online directory. And then, so think of that as the frame that I have to even choose my sample from. And then the sample is who actually ends up in your sample, who you actually end up getting information from. This will be a subset of your sampling frame. But thinking carefully about how these three sets overlap and or intersect is going to be an important piece in being able to assess the accuracy of your predictions. So we often want to be very cognizant about whether or not there are individuals in your sampling frame and or your sample that are not in your target population, and or vice versa. So because we're trying to take these samples to make guesses or inferences about the population, and again, inference here is drawing conclusions and quantifying their reliability. That's going to be a key piece of our framework. I don't want to just say, oh, well, I think the average height of all CU students is blank. I want to have some way to quantify how reliable my estimate is. How I draw the sample will affect the accuracy of my inference. We're going to think of error in our sample as split into two different categories. The first category is error that's due to random chance that's involved in the process of sampling. So on the next slide, I'm going to detail this in more, or to be more detailed in this, but I want to point out that we can, in theory, choose sampling techniques so that we can at least quantify this error, which is a great place to be. If I don't know how big or bad that error is, then it's very hard to be able to say, how reliable my estimate is. Now, bias is different than chance error in the sense that it's a systematic error in one direction. This can be the result of your sampling scheme and or your survey methods. The downside is we often can't assess the potential magnitude, as opposed to chance error, where in theory we're going to be able to at least model the potential magnitude. So for bias, it's really having protocols that we'll discuss in the next video, but some common things that you do when collecting data and or using data that's already been collected to make sure you're reducing the sources of bias as much as possible. Let's zero in on these different ways we can end up with chance error. So the most common way in our examples in this class is just from the fact that we're using chance to select a sample from our target population. So in principle, I could have gotten a different sample. So let's suppose that my target population exactly overlaps my sampling frame, which is kind of best case scenario. And then I take a random sample and I'm just going to visualize that sample as this. And inside here again are maybe the students I talked to, and so I get the average height of all the students in this sample. In theory, I could have gotten a different sample, right? And I could have gotten a different average height. That's just part of the variation that results from the fact that I'm not getting information from the entire population. Depending on how we select our sample, we'll actually be able to compute the magnitude of that chance error, which is going to be a very useful tool. Another way we can get chance error is when we are doing a controlled experiment and we're randomly assigning units to a treatment versus control group. And in this case, if we had split up the units differently, we could have gotten different results. Again, if we're doing this in a what's called randomized controlled experiment setup, which we will discuss in future videos, then we will actually be able to quantify our chance error. So that's another one where I'm able to at least quantify how off I might be. The last one doesn't show up in every possible sample. It really depends on what you are measuring. But if you're using some instrument for measurement and it does not have a bias, it is actually, right on target, and it has at least some type of distribution of errors that you can assume or model, then we can at least quantify the types of measurement error that may be contributing to our overall chance error. Again, this is more specific for data that we're getting using different scientific instruments. In the next video, we're going to deep dive into the different types of bias and see how we can potentially try to develop good practices and protocols to at least eliminate the bias as much as possible.